It's my pleasure to introduce Dale Pullin. Dale's currently the Carman Professor of Aeronautics at Caltech. He did his undergraduate degree in Sydney in aeronautical engineering, I believe, and then spent some time at Imperial College doing his PhD with Brian Spalding.
John Harvey,
I'm sorry, I've got it wrong. And then off to Caltech, where he's been involved in a great variety of activities, including rarefied gas dynamics, vortex dynamics, compressible flow, shockwave dynamics, stability, and of course, turbulence. So he's going to tell us all about Philip Saffman. Thank you.
Okay, thank you, Professor Davidson, for that introduction. I'd like to start by complimenting the editors on their vision for this project, and also on the patience and plain tenacity in actually seeing it through and producing a volume and this meeting, and also to thank them for the invitation to Dan Mayron, my co-author, equal co-author, and I to speak at this meeting on our friend and colleague Philip Saffman. So Philip Saffman, I'm not going to say much about him personally. Philip was I would say reserved but not quiet person. He was reflective. You could have a conversation with him. He was interested in politics, literature, particularly Shakespeare, and philosophy, but he would be brief rather than extensive. He was a family man who spent a lot of time with his family. His idea of sports was English rugby league and a bit of golf. And he was also had a very dry sense of humour. If I have time at the end, I'll tell you my favourite Saffman joke. So one interesting feature of this meeting is the different approaches to the subjects, ranging from the historical, biographical approach of Brian Launder to the blackboard and two-slide approach of Professor Frisch. My talk is going to be fairly technical. Philip Saffman is well known in many areas of fluid mechanics. Turbulence wasn't the only area he worked in, and in fact he's probably better known in other areas. If you look at his list of citations, he's citations in other areas such as flow in porous media, his famous work with G.I. Taylor, more cited than his turbulence work. He worked in vortex dynamics, bubbly and multi-phase flows, flow of dusty gases and water waves, but he did make important contributions to turbulence, which is the topic of this talk. So I'm going to really talk about mainly 6 papers from 1960 to a review article, rather strongly worded review article in 1978. Philip Saffman was born in the Leeds area of England in 1931. He came from a legal family. His father was a type of English lawyer known as a solicitor, and 2 brothers, Leonard and Simeon, were also solicitors. He described it to me that he was diffusion by continuous movement out of a legal environment to mathematics and fluid mechanics. He was evacuated to Blackpool during World War II with his family. It didn't seem to have much effect on his personal development. And he was something of a prodigy. He'd completed the entrance scholarship to Cambridge at age 15, but the university would not admit him, not because he was too young, but because he hadn't completed his military service, for which he was too young. So he had to wait, sit around the house, play a bit of golf, attended informal lectures. Why the English establishment couldn't have reversed it and allowed him to go to Cambridge first, by which he would have been finished in time to do his service, but that didn't happen. When he did do his military service, he entered the Royal Air Force, and I think he became a teleprinter operator, and he learned to type, something that he found very useful in the later age of emails and computers. He did enter Cambridge in 1950, completing the Tripos in 1953. The era of ranked mathematical wranglers had long passed, but I believe Philip was top of his class in an informal way. Then entered graduate study with G.K. Batchelor, and the way he described it to me was that Batchelor had, in conversation, had made the comment that you could tell good champagne from mediocre champagne because in mediocre champagne the bubbles went up, but in good champagne the bubbles rose in a spiral pattern, and Saffman did not know whether to take that seriously or not, so he decided that he'd better find out. So he engaged in research with Batchelor, although their interaction appeared to be minimal, and as far as I know, Batchelor and Saffman never published together. He worked with G.I. Taylor, but the famous work on Saffman's Taylor instability was later, after his PhD. He achieved the Trinity Prize Fellowship in 1955, which was unusual in the sense that this was actually won before he'd finished his PhD. So that is an indication that he was considered to be a person of considerable promise. Then was an assistant lecturer of Cambridge, after which he moved to King's College to join Herman Bondi's department in around about 1960. PhD thesis in 1966 was not on turbulence per se, but on some problems that are affected by turbulence, mainly the motion of drops, bubbles and particles in fluid. In particular, work with J.S. Turner looked at the spatial variation of fine-scale velocity driven collisions to try and estimate the distribution of particle sizes in turbulence. As I said, Saffman and Batchelor did not collaborate. Now, Dan Manor and I had to make some choices about what to include in a survey of his work on turbulence and what not to include, and we decided not to really emphasize this work, but Sayed El-Gabashi took me to task on that and said you really should have mentioned his work on flow of a dusty gas, so this is not in the actual article. Sproul in Nature in 1961 had claimed that the pressure drop required to drive the flow of a dusty gas through a pipe was reduced compared to that for clean air with the same mass flow rate. And Sproul, I believe, was involved in an experiment to obtain what he called the effective viscosity, and this involved the flow between rotating cylinders. He claimed that particles reduced the effective viscosity, and this led to decreased wall stresses, and that this was the explanation. But Saffman pointed out that this was inconsistent. This was a comment in Nature in 1961 in response to the Sproul article. Pointed out that this idea was inconsistent with an earlier theory of Einstein, that particles would in fact increase the viscosity, and that the real effect that Sproul was looking at was not due to a reduced viscosity, but could be explained in terms of the modification of Reynolds stress due to particle movement in the fluid. And he really had a back of the, well, it's more than a back of the envelope argument. He made an estimate of this for the experiment, which agreed pretty well with the experimental results. And Sayed El-Gabashi, in his keynote speech at the earlier meeting, emphasised this as important for later developments in particle turbulence interaction. Saffman attended the Marseille meeting in 1961, where he gave a talk on turbulent diffusion, at which he met Janos Laufer, who invited him to visit the Jet Propulsion Laboratory, where Laufer had a fluid dynamics group. And he went there in 1963, where he met Liebman and Whittam, who convinced him that he might find Caltech interesting, and he and his family decided to move there in 1964, where he joined GALCIT, called then the Guggenheim Aeronautical Laboratories of the California Institute of Technology. And then he later joined the newly formed Applied Mathematics group, who with Lagerstrom, Julian Cole and Whittam had broken off from GALCIT, and Saffman joined them. He always remained through his career at Caltech Professor of Fluid Mechanics and not Professor of Applied Mathematics. He was elected to the Royal Society in 1990 at age 59, which always struck me as a bit late given his clear preeminence by that age. He became the von Karman Professor in 1995 and he retired in 1998. He had colleagues in GALCIT who were very interested in turbulence, mainly Liebman, Anatole Roschko, Don Coles, and also Gary Brown, but he didn't really interact a lot with them. I think he talked with them regularly, but there was no evidence of great collaboration. So this is a photograph slide from the Caltech catalogue, which lists classes, September 1966. I couldn't find a 65 catalogue, but I did find the 66 catalogue, in which Saffman is listed as giving lectures on homogeneous turbulence, and one can see that one of the topics is properties of the large eddy, the fine-scale structures of turbulence. So he was lecturing on the topics which he later did seminal research on in the mid-1960s, soon after his arrival at Caltech. So perhaps his first real contribution to turbulence was to look at the effect of molecular diffusivity on the mean square displacement of particles with reference to molecular diffusion of a conserved scalar. Of course, Taylor had showed in 1922 in his famous paper by diffusion by continuous movement that the dispersion was related to an integral of the Lagrangian two-time correlation, which for homogeneous turbulence could be simplified to a single integral related to the Lagrangian autocorrelation coefficient. Saffman looked at a similar idea, but for a conserved scalar, which in the continuum approximation was subject to molecular diffusion. And if you consider the two effects separately, the Taylor diffusion by continuous movement and diffusion, you get just a simple addition of the two terms, but I think it was accepted and well known then that would be an interaction between the diffusion and the Lagrangian motion. And Townsend analysed this using for I think the wake of a thermal plume from a point source, and found the correction due to the interaction was a positive contribution proportional to t cubed times the mean square vorticity. So the interpretation of this is diffusivity tends to accelerate the dispersion so that the turbulence increases the rate of increase of a heated fluid volume. Saffman looked at this from a different perspective, and his view of it was that you really had to include both the continuum motion but also the underlying random Brownian motion. And he looked at this, analysed this in terms of what he called a substance Lagrangian autocorrelation coefficient, which included correlations between the macroscopic motion and the Brownian motion. And this was quite a delicate calculation described in his paper, in which there are correlations between the Brownian motion, molecular motion, and the continuous macroscopic motion at a slightly earlier time. And he calculated this by a local solution using a representation of the velocity field with local straining and rotation, and he got a quite different result. He found that the correction was of the opposite sign with a different coefficient, so that his interpretation was the molecular diffusivity actually decreases the dispersion, so that the average velocity of a blob of scalar actually decreases as the volume increases. And this is a bit counterintuitive. Saffman, I know, considered this to be one of his more interesting contributions because he considered it to be a genuine prediction. The answer was not known. He made a clear distinction between prediction and post-diction. Post-diction, when you do a calculation or develop a theory and you already know the answer. It could be easier to get the answer, but true prediction, you just don't know. You've got to take a risk. He considered this to be a true prediction. As far as I know, it remains an open question. It's a higher order correction, so the experiments are very difficult. Experiments by, I think, Michelson and McKelly are in conclusion. It's an open question, so any young experimentalists who want to address this issue, here's an interesting problem. Saffman didn't always get it right. He was a wonderful intuitive thinker, but sometimes he didn't quite get the complete picture. He looked at passive vector fields. Vector fields are interesting, describable by the two equations. Two types of vector fields, one described by the F equation, an example of which could be a magnetic field in a kinematic description of magnetohydrodynamics with no Lorentz forces on the fluids. The magnetic field satisfies an equation like the F equation. F, of course, is divergence-free, and lambda is the ohmic diffusivity. Another example would be if lambda equals 0, F would describe the statistics of infinitesimal line elements. G is another example, the gradient of a passive scalar, and the G equation is very easy to describe by just taking the gradient of the scalar advection diffusion equation. So Saffman was interested in this problem. Batchelor had earlier worked on the equivalent problem for a scalar. Saffman worked with the 2-point correlations of the F field, F and 2-point correlations of the G field, and he made certain physical assumptions and modelling for the higher order correlations. You can derive a Kalman-Howarth-like equation for the correlations under the assumption of isotropy, and again he modelled the solution of the appropriate equations by using a velocity field that was linear velocity field with based on the strain eigenvectors of the eigenvalues of the strain field Sij, and he modelled the third order correlation, and he got a number of different results, and the details are rather technical. We don't really need to go into them with too much detail, but he, I think, correctly concluded that the statistics of F squared and G squared depended on the statistics of the eigenvalues of the rate of strain tensor, some information which was known at that time from experiments by Batchelor and Townsend. Of course, he didn't have the advantage of modern DNS. He got several results depending on assumptions made. He recognised that under one set of assumptions, F squared would diverge, but he preferred a different set of assumptions in which he concluded that F would be stretched and compressed almost equally, but when it was compressed, ohmic diffusion would be enhanced, and this would suppress the ultimate stretching of a vector field, and that both F squared and G squared would decay. He concluded there was no sustained dynamo. It turned out to be correct for the G field, but not for F. It was pointed out by Moffat later that F squared can and will grow under certain symmetry assumptions when the helicity is non-zero. So this is a problem that he really didn't quite get the right answer, and you really need to read the paper carefully. There are delicate balances in some of his assumptions, and it's probably he should have, I think the correct answer was his earlier of two scenarios. The passive vector field is an interesting problem. Your passive vector field can be considered such with all initial conditions except one. There's one special initial condition on the passive vector field. If you put it equal to the vorticity and lambda equal to nu, then it will not stretch indefinitely because it will behave exactly as the vorticity does. So in that case there is different behaviour, but it has measure zero in the space of the possible initial conditions. This was looked at by Okatani in detail, and Sonoba and Galanti also by CFD, but it's now known, of course, that F squared will grow in general. Theory of homogeneous turbulence, he was working on this in his early years at Caltech, and he produced he was invited, I believe, to give 10 45-minute lectures at an international school on nonlinear physics in Munich in 1966, and these were later published in 1968. And it was basically a 100-page tract on homogeneous turbulence, which is prefaced with the remark, a somewhat famous remark, that homogeneous turbulence is a theoretical idealization. And it's been said with too much truth for comfort that the purpose of homogeneous turbulence is to provide full employment for mathematicians. I don't think he had any problem with that. He believed mathematicians should be fully employed. He was in a very experimentally oriented turbulence group with Roshko, Coles et al., and they probably gave him a bit of heat for concentrating on homogeneous turbulence, but he felt homogeneous turbulence was interesting, that it simplified some of the problems of trying to understand inertial range turbulence, and that it was worth studying. And he made a major effort to look at homogeneous turbulence, and I think of his work the most interesting is probably the right now celebrated work on the large eddies. This is a very subtle problem, been visited earlier by others, and in late 1930s, I think 1939, Leuciansky formulated the so-called Leuciansky integral, which is the second moment of the two-point velocity correlation, which under isotropy can be reduced to the integral of r4 times fr, the normalized two-point correlation, which can be related to the square of the angular momentum in the fluid of volume V. For large V, the Lorentziansky invariant goes as m squared on V plus a correction. Under certain conditions, the Lorentziansky integral was shown by Lorentziansky himself to be an invariant of the motion, and if it exists for turbulence, then it's relatively easy to show that the energy spectrum for large k, the leading order term, has to go like k to the fourth. For existence, of course, then the normalized two-point longitudinal correlation has to decay sufficiently rapidly. Landau argued further that if the Lorentziansky integral exists, he made order of magnitude estimates that I goes as u squared times L to the fifth, plus with the additional assumption that the dissipation is independent of Reynolds number, you can get out that the energy decays as t to the minus 10�7th, while the integral scale grows as t to the 2/7th. However, Batchelor and Proudman had cast doubt by arguing that fr could decay as r to the minus 5, and that's not so good news for the Lorentziansky invariant, because it shows that the integral is only conditionally convergent. In fact, it may even diverge. So Saffman revisited this problem. He argued that the really important thing in looking at the Lorentziansky invariant was the initial conditions, that is to say, the velocity field at time t equals 0 that's going to lead to the decay. And he was thought very physically and said we have to think about how these initial conditions are generated from a fluid at rest. He formulated this problem in terms of a spectrum of, or a distribution of impulsive forces at time t equals 0, and specified the properties of this impulsive force distribution, namely the spectral tensor, the force correlation exists, and that the two-point correlation decays exponentially with increasing distance, both of which seem reasonable assumptions. And he showed that under those assumptions, the vorticity spectrum tensor and the energy spectrum tensor take certain forms in which they're proportional to a tensor script m alpha beta, which is related to another tensor mij, which is in turn related to the angular momentum. And he could, the linear momentum. So he, Saffman, concluded that under conditions where the mij tensor, or components, were not equal to 0, that E of k, in fact, for the large eddies, the leading order term should be 4 pi mk squared plus higher order terms. And this has consequences for the Lorentziansky integral, because if this is the case, it's easy to show that u squared fr must go as m on r cubed, and with m on r cubed, it's clear that the Lorentziansky integral does not exist. So the generation of initial conditions is crucial for large eddies and decay. And Saffman at the time thought this was interesting, but perhaps of no real importance, but it turns out later that it is important. He makes the comment, the work on the structure and invariance of the large eddies is to be believed to be both new and correct, which indeed it was, but of no real importance. But this problem was revisited later by Professor Davidson, who distinguished between two types of turbulence. One, the initial conditions are such that the Lorentziansky integral does exist with negligible variation, in which case Landau's estimate is the proper decay law. The energy decays as t to the minus 10⁷. And Saffman turbulence, where Lorentziansky integral doesn't exist, and in which case leading order spectrum is k squared, and a different decay law, t to the minus 6/5 results, and L goes as t to the 2/5. So there's been quite a lot of work on this. In particular, a very interesting experiment by Krogstad and Davidson in a very large wind tunnel shows that the decay is closer to Saffman turbulence than Batchelor turbulence. The difference, t to the minus 1.13, could be because the dissipation decays slightly. So this is, it may be possible to produce Batchelor turbulence, but in this wind tunnel it was Saffman turbulence. Saffman was interested also in the physical structure of turbulence, and he explored the idea of applying the arguments that leading to the k to the minus 5/3 for 3D turbulence to another form of turbulence sometimes called Burgerlance, which is random solutions of the viscous Burger's equations. And he pointed out in his lectures that the Burgerlance had many features which were rather similar to 3D turbulence. There was a separation of small and large scales. The dissipation was independent of viscosity. Shocks formed. Dissipation was independent of viscosity. Energy is conserved on particle paths, and you could certainly use similar arguments to conclude that for Burgerlance, the energy spectrum is k to the minus 5/3. But it's wrong. It's completely wrong. The reasons are pretty clear when you think about it, but it's not, again, the arguments are very similar. For Burgerlance, shocks form which determine the statistics of the small scale. Burgers had earlier argued that if this is the proper structure of Burgerlance, that EK should go as k to the minus 2 for scales greater than the smaller than the separation between shocks and greater than the thickness of shocks. So Saffman argues that for Burgerless turbulence, if you look at the there is a Kalman-Houth equation for Burgerless turbulence, which looks almost exactly the same, except for coefficients for 3D turbulence. But of course, the skewness is not a constant, unlike 3D turbulence, where the skewness is a constant independent of has a weak dependence on Reynolds number. For Burgerlance, the skewness is a strong function of viscosity and is not constant. The small scales are determined by the properties of shocks across which there is flow. So the nature of the singularity or the incipient singularity in Burgerlance and 3D turbulence are quite different. One is dominated by shocks, the other perhaps by vortex sheets for which there's no flow across the sheets, but there's flow parallel to the sheets. So his point was that you can easily get wrong results by naive arguments. He was also interested in the physical mechanism of cascade in 3D. I think it's fair to say that he preferred a physical mechanism of, he preferred a structural picture of turbulence rather than a wave number space picture. He proposed a hybrid structure which has some similarity between that discussed by Professor Hunt on Thursday. There were two parts of this. For the first was what he called the primary cascade. He saw big scales as blobs or spheres of fluid which were stretched by the strain rate of other structures into sheet-like structures with a certain length scale, UL over nu to the half. He was able to estimate the volume fraction of these sheets and also the dissipation, but the dissipation is not independent of Reynolds number. So to correct this, he proposed what he called the secondary cascade on sheets. So this is the smaller scales, and he proposed that since sheets are likely to be curved, particles are moving in curved trajectories will undergo a Gertler instability, and that the Kolmogorov scale is actually the thickness of the boundary layer between the cells of these Gertler motions, and out of this he was able to extract a Kolmogorov length and a dissipation that was independent of Reynolds number. Of course, this model was really rather simple, perhaps too simple. He was unable to put it in quantitative form. One of its great weakness, of course, is it didn't predict the skewness, the art of the 2/3 law, equivalent to k to the minus 5/3. Saffman also worked on two-dimensional turbulence. It's well known, it was known then there was no energy cascade in 2D turbulence below the forcing scale. It's pointed out by Professor Frisch, there's an inverse cascade. But for scales below the forcing scale, at large wave numbers, Kreisner and Batchelor had argued that since vorticity is conserved on particle paths, there will be a vorticity cascade and not an energy cascade, leading to dimensional arguments can give you the vorticity spectrum from which you can back out the energy spectrum, and this gives you k to the minus 3. Saffman argued, had a different argument. He said for 2D, turbulent field would tend to develop near discontinuities in vorticity, and that the length scale of these vortex jumps would scale on the inverse third power of the mean square vorticity. So his picture of 2D turbulence was something like piecewise constant vorticity with discontinuities, which gives k to the minus 4, which is different to the creation and Batchelor k to the minus 3. To the best of my knowledge, this remains unresolved. I think it's one of these problems where initial conditions are important. One has to look at the space of all possible initial conditions. There are certainly initial conditions for which k to the minus 4 is correct. Piecewise constant vorticity when nu is equal to 0 will always have a k to the minus 4 spectrum. It's not clear that vorticity jumps, however, are in general an attractor in 2D flows when nu goes to 0. So I think that to some extent is an open question. So now to Saffman 1978, I'm going to finish by discussing this paper. This was I think an invited review paper in the late 1970s. This was some 25 years after Batchelor and Townsend's monographs on turbulence, and there'd been some real advances. DNS had been formulated, first spectral calculations of homogeneous turbulence by Warsaw had been done. PDF theory of turbulence had been formulated by Lundgren and Monen. There were systems dynamics ideas in turbulence, vortex dynamics, or vortex methods had been created. The main ideas of large eddy simulation were in place, and Saffman undertook a review which was presented at this meeting, I think, in Berlin. Here is the program. Professor Riley was there and probably has vivid memories of this, so he followed on from Saffman. So Saffman, this is an interesting article. I've never seen anything quite like it in the turbulence literature. It's rather forthright and critical, and it hasn't really been widely cited, perhaps for good reason. So Saffman reviewed progress since the 50s. He discussed the properties of a desirable theory in ranked decreasing importance. To him, the most important qualities were clear physical and engineering purpose and intelligibility. It had to be reasonably intelligible without a vast amount of work. Predictive capability was in the middle. Rigour and originality were pretty low down. He made the comment that a theory which cannot be understood without enormous effort would seem to lack value. It had to be reasonably intelligible and accessible without enormous amount of effort. He made the comment that practically everything that's useful in turbulence is a scaling law, and that could be viewed as continuing today, the search for new scaling laws. But he also qualified that by saying this did not work well for complex flows, as outlined in a contemporary article by Peter Bradshaw. He liked vortex-based methods and proper orthogonal decomposition had been introduced around that time. He thought that these might be useful. He characterised RAN, I think, a very interesting and correct characterisation as an interpolation of experimental data, which I think is, he worked on RAN's problems, RAN's related problems. One of his students, his name escapes me right now, Wilcox, I think, developed omega K models of turbulence. So he estimated the DNS operation count as a function of Reynolds number. I don't think this is original. I think Liepman had done it earlier, and commented that this is a pretty steep function of Reynolds number. DNS for real flows geometry are awaited with interest. Interesting comment. I think there's been some progress there, but we're still waiting for flow past a sphere at the critical Reynolds number of 300,000 by DNS. He made the comment subgrid and vortex modelling as assessed as really combining heavy computing with approximations of unknown validity. So he thought that was interesting, but all a bit ad hoc. But he did make the comment that the real problem with LES is handling walls. If LES can produce the log layer and the Kalman constant, then a practical method of calculating the gross details of turbulence will be available. But at the time, LES was in its infancy. The idea was there, but it hadn't quite assumed the importance or the role in turbulence it has today. And you could see that in the previous 13th conference, where there were quite a few talks on LES. He did review contemporary theoretical approaches, and he wasn't too positive about them. I'm not going to say anything about this. You can read the article yourself. It's not easy to find online. If anyone is interested, please contact me and I can send you a copy. Also, if you're interested in the lectures on homogeneous turbulence, which are a great resource, again, they're not too readily available online and I can provide a copy of them. I don't know whether it's legal to go. Well, I'm almost done, so I'll finish early. That's good. He did pose 7 interesting questions, which are listed here. One of them, 2 of them which are important, I think, still important and are not resolved. For number question 1, is the energy dissipation rate of homogeneous turbulence really independent of the viscosity as nu goes to 0? And that was a question of pressing importance at the time because it's used in assumption in the development of many different models. And that is a question which I think is still with us today. There has been experimental work, a lot of experimental work, including some experiments by Professor Srinivasan in the early 80s, which certainly gives support to this for certain types of turbulence, but is this a universal feature? For example, the turbulent flat plate or rough wall turbulent boundary layers, the Reynolds number goes to infinity. Is that the case in that flow and for other flows? That is one of the 7 questions which I think is still an open question. Number 6 is this concerns questions of the long-time existence of solutions of both the Euler and the Navier-Stokes equations. The question of long-time existence of Navier-Stokes equations, to the best of my knowledge, is still open. There's a Clay Prize of $1 million, which pre-2000 seemed like a lot of money, but that is still unclaimed. To the best of my knowledge, there's no proof of long-time existence from continuous initial conditions for either the Euler or the Navier-Stokes equations. There are some results. I think there's the shadow theorem of, I believe it's Constantin, that if singularities do not exist, if you take an initial condition for both Euler and Navier-Stokes, and if there are no singularities in Euler up to a time t after the initial condition, then all Navier-Stokes flows will converge to the Euler solution when nu goes to 0, but it's dependent on a strong assumption that there's no singularity formulation for Euler. So I believe that these are still 2 open questions. I think the other questions work has been done, and you can make up your own mind on whether these are resolved or unresolved for turbulence. Finally, I'm going to finish a little early, but there'll be more time for questions. He concluded his 1966 lectures in the written version. I think he was rather frustrated. He'd spent more than 10 years working on turbulence and felt that he hadn't made much progress and that neither anyone else had made much progress. So he made the rather trenchant remark in analogy with what he used a quote from Macbeth. Finally, it would seem that turbulence theory to date can be summarised by the quotation from Macbeth, full of sound and fury, signifying nothing, which is a very strong statement indeed, and it's to be hoped that future work will render this quotation inappropriate. So he was not really happy with progress made, at least on the theoretical side of turbulence. I think he felt that turbulence was a very difficult problem, that the theories had not really penetrated to any depth, and that there perhaps wasn't the universality that he'd hoped for when he first started out. By 1978, he makes another comment in finishing the 1978 review article, which I think is a much softer version of this. In searching for a theory of turbulence, we're looking for a chimera, so perhaps there's no real turbulence problem, but just a large number of turbulent flows, and our problem is the self-imposed and possibly impossible task of fitting many phenomena onto the Procrustean bed of a universal turbulence theory. So I think he was a bit concerned that turbulence research had kind of fragmented into a kind of taxonomy of turbulent flows, and that there really wasn't the degree of universality that earlier workers had hoped for, so that there was really no turbulence problem. There was just an infinite number of problems and flows depending on initial conditions and boundary conditions, all of which were different and did not really show any common or universal features. We'll just finish there, but just show this is a picture. Any of you have been to Los Angeles and you've looked around the streets of Beverly Hills, you'll notice many, many palm trees, and all the palm trees are straight, and some of them are extremely tall. But this is Saffman's palm tree, and Saffman's palm tree, of course, had to be different. Saffman's palm tree looks like a vortex filament. He didn't grow it that way. I think it was there when he came. So his is, I've never seen one like this. I've seen thousands, if not tens of thousands of palm trees in Pasadena, but this is Saffman's palm tree, and it's a vortex filament. And apparently this was so well known in the area that busloads of tourists would come down Nonita Drive, and the tourists would get out and photograph the palm tree, and he had to contact, I believe, bus tour operators and ask them really to desist from this practice. But the palm tree remains there today. His wife, Ruth Saffman, Philip passed away in 2008. His wife, Ruth, still lives at 399 Nonita Drive. The Saffman palm tree is still there. If you're ever visiting Pasadena, it's a very short walk from Caltech, and you might want to go and have a look at it. And I'm sure one by one a photograph would not be unappreciated. I've always called it the vortex tree. I don't know if it satisfies the local induction approximation, probably not. So that's Philip Saffman, a dear friend and a colleague. I've only covered his work up to the 70s. He did many other things, turned to Turbulence later. He did many other things for which he's very well known, and he's sadly missed at Caltech. So I'm just going to finish by making a reference to the next talk by Professor Moffat on George Batchelor. So Ivan showed a photograph earlier. Ivan and I decided we'd go and look and try and find Batchelor's house and see if there was a plaque or something. So we actually got the address. I think it was in one of Professor Moffat's emails. We didn't know the address, 107 Eglinton Street, Mooney Ponds, and we went there. And unfortunately, the house has been demolished. So we'd hoped for a plaque, but there's nothing left. I think the house Batchelor lived in was probably more like this rather modest bungalow than this mansionisation that's so common in the suburbs of many cities. But we took a photograph of each other, so we have memories of George Batchelor. So that's Batchelor territory, probably in the 1930s. So I'll finish there, and I'd be happy to, of course, answer any questions. And thank you for your attention.
So wonderful lecture, thank you very much. I love the picture of Saffman, it's just great.
Yeah, it is
and
a nice shot.
The quotation at the end is very nice, I think. So we have plenty of time for questions. Grisha.
Just a short remark and a couple of questions. A short remark, this Landau quotes 10/7, this law of decay of turbulence, for Kolmogorov. It's Kolmogorov did it, and Landau in his book ascribes to Kolmogorov. And two short questions. First is this, he's mentioning theory which is require enormous effort to understand.
Yes.
Its job at Krajknan, Edwards, I mean, just maybe you know at whom specifically he meant. And second, what he thought about turbulence at 90s. Do you have any trace of his thinking about turbulence or estimating what others did?
Well, I think the answer to your first question, of course, you should read the article, since you asked. I think he felt that the statistical theories just took an enormous effort to understand. He thought that, remember at that time, I think that was the time when the accretion theories produced a -3/2 instead of a -5/3, and that the effort was perhaps not rewarded with physical insight. He found the details a bit obscure. He didn't like some of the language. I think this was largely a matter of taste. But I think the real reason is that Saffman preferred a structured approach rather than a formal.
So it was about statistical theories.
Yeah, he did not like the statistical theories very much indeed. So, your second question about in the 90s, well, I worked with Philip in the 90s, and again, he returned to look at structural models of turbulence. And he particularly liked the Lundgren spiral, which he thought was really very nice. He understood that it wasn't perfect, that you probably didn't see it literally in turbulence, but he felt that contained enough of the physics to be the best structural model available, in that it went a little bit beyond the generalized, well, I don't want to call it hand-waving, but scale arguments. He thought, in fact, that in his model, maybe the spiral would replace the Taylor-Gertler vortex. So he returned to, I think, thinking about structural models.
I tried to incorporate those spirals into statistical Krasner-like series, and it is very difficult. But I think that these spirals, they have future. Technically, trying to incorporate them into statistical theory is very difficult. I particularly failed trying doing this, but I'll maybe try again.
Okay, well, that would be very good. Yes.
Well, just a comment on the spirals. You mentioned, of course, the apparent conflict between the Batchelor, or the entropy cascade, and the Saffman's theory. There is an intermediate theory, which was Gilbert's theory, where these patches, Saffman-type patches, can wind up into spirals. And then you can get any power law you like, more or less, between the -4 and the -3.
11/3.
Okay, we have time. There's one at the back there, I think.
So many of us who do not know Saffman personally tend to associate him with his famous monograph on vortex dynamics. So I'm just curious, in what sense did his fundamental work on vortex dynamics inform his research on turbulence?
Well, I think it was the other way around. He worked on many aspects of vortex dynamics. After he left turbulence research, one of the areas he worked in was in vortex dynamics, and he did quite a lot of work in a rather celebrated collaboration with a man named Derek Moore, a very fine applied mathematician. And I think his work with Moore really stimulated, and his work with students stimulated his interest in writing a book and putting down some of the various approaches to vortex dynamics, at which he looks at tubes and sheets and the idea of impulse. So I think the book was really an account of the various territories in the dynamics of interacting and vortices that he'd worked on in the period probably from late 1970s through to 1990. I think he wanted to put it down. There was no equivalent textbook at the time, and there were many results that he really did that were not even written up in papers that he and Moore knew about, and he really wanted to put them down. I think the work informed the textbook. Yeah.
Okay, thank you. One last question? No? Okay, perhaps I can just make one comment. Someone yesterday in the discussion, I think perhaps Nick, said, what does DNS bring to the game? And for me, I think it's revisiting Philip Saffman's view that we need structural models. It gives us the opportunity to look at vortex dynamics again in the context of turbulence. That's what DNS brings for me. Thank you very much.
Okay, thank you.